Today, Data Communications and Network 1 class is lecture 11. It will be on chapter 5, Error Detection and Correction, part 2. And we will start with the encoding by the chip register circuit. Okay? Last time we talked about the encoding by binary sequence and by the polynomial. So this time the chip register circuit can be used for encoding the code word. Okay, the register have to contain n-k bits, which is the length of the FCS or the frame check sequence. And the circuit is constructed based on the generator sequence or the generator polynomial gx. For example, if gx is equal to 1 plus x cubed, the corresponding chip register is like this. You can see that the left-hand side is the least degree of x. Okay, so x to the 0 is the left-hand side, and x to the 1, x to the x squared, and x cubed. I will show you here. You have gx is 1 plus x cubed. What you do is that you have this is equal to n minus k bits. Okay, so you have to have a register circuit which is 3 blocks. This is equal to the number of blocks in the circuit. Okay, so when we have 3 blocks, this is x to the 0, x squared, and x cubed. Okay, so when you have, if you have a term, okay, that term you will have a line connecting that at that position. Okay, when you have x, you will have a line coming. Okay, like this. And then you don't have the x squared term, so there is no line coming here connecting. You have x cubed, so you have the line coming here. Now, when you combine these together, if you have two arrows coming, okay, you have to have an operation. So the operation is modulo 2 addition, or so this is modulo 2 addition, or is XOR operation, okay, exclusive OR. If you have only one arrow coming out, okay, you just go like shift to directly to the other blocks. This one, okay, at the rightmost side, we will input the data at this position, okay. Suppose the data is M, okay, the data sequence is M. So we will have the 2 of these coming in, shift in here, okay, and then data coming in. So you add them together, modulo 2 addition or the exclusive OR gate, okay, the same thing. Then you have the output coming out here, and it got feedback into this, okay. So this is how you construct the chip register circuit, okay, for encoding based on the generator's polynomial. If this is different, okay, if there is, you have x1 plus x squared plus x cubed, you will have this line and then this line, okay, but not this one. So you have this line instead over here, okay. So, for example, if you have anyway, so let's see, okay, you have this one is x squared, x to the 0, this one is x to the 1, this one is x cubed, and that's why you have this line, and then this line, okay. The generator polynomial is depend on the code, okay. Usually you will have a specific value of generator polynomial. For example, if you have a circuit code, okay, such as a BCH code, you will have the generated polynomial that is kind of, you have to find the generated polynomial that there is a specific method to find them, okay, which is beyond the scope of this class. However, the BCH code, you will have like 7-4 code, 15-7, 15-11, something like this, for example. So in this case, you have n minus k equal to 3. In this, n minus k equal to 8. In this case, n minus k equal to 4, okay. So this is the degree of g of x, okay, for this code of the BCH. So again, BCH code is a class of cyclic code, okay, that is used a lot. Now, when I want to encode, okay, what do I do? Okay, I have to input the, suppose I use the same, okay, the same GX, and I have the same circuit here, and I have the data. The data is 1110, okay, which is M. And this data, the 1110, the first one is the left-hand side is the most significant bit. This is the most significant bit, and this is the least significant bit, okay? MSB is most significant bit. Okay, anyway, so when I put the data in, okay, at first I have to initialize. So initialize the value in the register, okay, so they are all set to 0. Then when 1110, okay, coming in, when 1 coming in, what happened? 1 is here, this is tipped out as 0, 1 plus 0 is 1, feedback over here, so this is 1, okay? This is 1, and then this is also 1. So after the shift number, okay, after you first you shift it one time, okay, you get this. This one is shift over here, 0 shift over here, so you get 0. Then, okay, this one already get in. So what you have left is 110, okay. So you have 110 left. This one already get in. Now this one coming in. So you have 1 plus 0 again, because this one shift out of the register. So you have 1 plus 0 equal to 1 again, and you shift here. So after the second shift, you get 1 here, and this one coming out, okay, so this is 1, this is 1 again, so 1 plus 1 is 0. So at this point, you have 0. And then this one, you just shift, okay, you just shift directly. So this one is 1. So this one already get in. Now you have 10 left, okay? Okay, so this bit get in, so you have 1 here getting in, and then in the chip register, this is 1, okay? So chip out, 1 plus 1 is 0, so you shift out as 0. So after the third shift, you have 0 here, okay, and 0 coming in here. So 1 coming out plus 0, you get 1. This is shift like this, so you get 0, okay? So this one already get in. Then the next bit is 0. So 0 plus 0 is 0, right? 0 plus 0 is 0. So after the fourth shift, you get 0 here. And then 0 plus 0 is 0, okay? And this one is shift. Okay, so all of the bit has already get in, okay, inside of the circuit. When all of the bit is has been input into the circuit, okay, you will have this. This is the result in the chip register, okay, so in the chip register. And this one, you can see that this is the least significant bit, and this is the most significant bit, because the least significant bit is on the left, okay, because this one is X the lowest degree of x, right? And this is the highest degree of x is at this position, okay? So this is most significant bit. This is, this is most significant bit on the right, and this is the least significant bit on the left. Okay, so the code word for this case would be V equal to 2 to the n minus k u plus the frame check sequence, okay? And this one is 1110, right? That is shifted by 3 bits to the left because it's multiplied by, so this one is multiplied by 2 cube, okay? So shift to the left. And B is the parity check bits, okay, or the frame check sequence. And we just compute, okay, that the B, okay, from the, okay. So from here, you see that the most significant bit is 1, right? And the least significant bit is 0. So you have the frame check sequence or B as 1, 0, 0. If this is the most significant bit and this is the least significant bit. Okay. You can see that you have to be careful that this is most significant bit. So when you write, if you write the most significant bit on the left, it has to be 1, 0, 0. Okay? So when you put it here, 1, 0, 0, and this is the most significant bit, and this is the least significant bit. Okay, so it has to be in the same order. Okay, so if this this is start with most significant bit of data, then the check have to be also start with most significant bit. Okay, so it's going to be 1, 1, 1, 0, and 1, 0, 0. So if you compare with the last time, okay, we get the same code word. Okay, from the other methods, from the method of the binary sequence and the polynomial. When we are done with the encoding, then we will continue with the decoding, okay? Now let's look at the procedure a little bit, okay, on the encoding. We will check the data in from the right, okay, into the chip register, and we will shift until the last bit of data is in the leftmost position, okay? So this means that the next chip will give us the remainder, okay? So basically we will shift, okay? We will shift the data in, okay, until all of the data is inside of the circuit, okay? So you don't have to worry about this. We shift the data in from the right and shift until the data, all of the data is get inside of the circuit, okay? And then you get, for the last tip that the last bit of data coming in, then you get the frame check sequence or the priority check bits. Okay, and this one says that when you cross the boundary, if the leftmost bit of the last tip is 1, then you change the value of the crossing bit. So this is kind of a technique, okay? Like this. It's kind of a shortcut, okay? So you can do what I said, or you can do something like this. If you have a link, okay, at this point, you can draw kind of a boundary here, okay? This one has no boundary because there has nothing coming down. So when you cross the boundary, okay, if the bit coming in is 1, the bit feedback bit, okay? So the feedback bit is 1. This is 1 coming in. If it's 1, then you have to shift. You have to change the value from 0 to 1. If it is 1 again, you have to change the value from 1 to 0. But if it's 0, okay, you don't have to change the value. If it's 0, you don't have to change the value. So this is the same value because the feedback is 0. But this is different value because the feedback bit is 1, okay? So anyway, this is just to tell you that if this is a boundary, you have to be careful whether the value will change or not. However, if it is not a boundary, if it's like this, that shift together, then these bits are always the same, okay? The one before the shift and after the shift will always be the same because there is no link going down, okay? But in this case, because there is a link going down, the feedback bit can be 0 or 1. So you have to be careful at this point. This is the standard, okay? CRC 16. There are a lot of cyclic redundancy check code, okay, that use 12 or 16 or 32 bits frame check sequence. So, and as I told you before, so the generator polynomial is specific, okay? It has to be like, this is a good code, okay, and the GX should be like this. The remainder from all three methods have to be the same, okay? Now let's look at the decoding. The decoding is done at the receiver. When you want to check the errors, okay, the receiver will divide the receive sequence R by the generator sequence G, okay, and this G should be bold, okay, because it's a vector G. So we have to check or test, okay, whether the remainder of the receive sequence divided by the generator sequence is 0 or not, okay? If the remainder is equal to 0, you will assume that there is no error, okay, or no error is detected. So even if there is some error, which is very low probability for good code, okay, but it is not 0. I mean, the probability that you will have undetected error is not 0, okay? Because if one code word, okay, is disrupted by the error and make it look like another code word, then the receiver will be full, okay? The receiver will think that there is no error. Anyway, if you design a good code, this probability of undetected error is very, very low, okay? So this is the best you can do. If remainder is 0, you say, decoder say no error. If remainder is not 0, okay, then definitely you will detect the errors. Now, why do we do this, okay, in order to check the error? Because at the encoding, if you remember, at the encoding, we add the frame check sequence so that the code word that was transmitted is always divisible by G. Okay, if you remember at the encoding, we do something like this. Okay, we find the frame check sequence and then we send the code word, okay? And the code word is the thing that must be divisible by G, by the generator sequence. So you know that every code word that was transmitted is divisible by G, by the generator sequence with no remainder, okay? Make all code words divisible by G, okay? So decoding checked whether the receive sequence is divisible by G by finding whether the remainder of R divided by G is 0 or not. Okay, so encoding, you make all code words divisible by G, okay? So remainder is equal to 0 when you divide R by G, when you divide code word V by G, okay? So at the decoding, you checked, okay, whether this is true. If this is true, it means that what you receive is a code word. So you say, okay, if it's a code word, then you say no error occur, okay? However, it is still possible. So, okay, if remainder of R divided by G equal to 0. So you have to receive a code word. However, a code word, this code word doesn't have to be the same as the transmitted code word. It is possible that you send V1 through a channel and you receive V2, okay? And both of these are divisible by G. And in this case, you get undetected error. In order to have very low, we want low probability of undetected error. So we need to use a good code, okay, or a good error correcting code, or error detecting code, okay. If you only want to be able to not be fooled, okay, you use good error detecting code is okay. But if you want to be able to also correct the error, okay, then you want good error correcting code. However, if the remainder is not 0, then you must detect an error because the received sequence is not a code word, okay, it's not in the set of a code word. Okay, as I said before, if the received sequence contain no errors, it will be the same as the code word, okay? So we decide, okay, that the remainder of V over G is equal to 0 because it's V divisible by G, okay? Then the remainder of R over G, if R is a code word, they have to be 0 too. Now, there are 3 ways to check whether the remainder of R divided by G is 0 or not. The first one is by modular 2 arithmetic. The second one is polynomials. The third one is digital logic or chip register circuit. These are the 3 methods as has been done in the encoding part, okay? Now let's look at the difference between the decoding from the encoding. First, we will operate on the received sequence R instead of the data sequence U, okay? So instead of putting U to find the frame check sequence, we will put R in, okay, and find whether there is divisible by G or not, okay? So the first one, the modular 2 arithmetic, suppose G equal to 1, 0, 1, 1, okay, and R equal to 1, 1, 1, 0, 1, 0, 0, okay? We have to define that the left-hand side is least significant bit or most significant bit. In this case, the left-hand side is most significant bit, okay? Left-hand side is most significant bit. So when you divide, you will put the most significant bit on the left. So for the R, you divided R by G, right? So inside of the numerator, okay, is 1, 1, 1, 0, 1, 0, 0. And then the denominator is 1, 0, 1, 1. So you divide in the same method as what you did in the encoding, okay? So when you divide this, you will get if there is if the result is 0, then it means that it's divisible by G. But if the result is not 0, then it is not divisible by G and errors is detected. If in this case the remainder is 0, okay, so it means that the received sequence is a code word. In this case, if the leftmost bit is the most significant bit, okay, you would know that the 4 leftmost bit is the data, okay, it's a 4-bit at the 4-bit data. So the data will be decoded as 1110, okay, the first 4 bit of the received sequence is 1110, okay. The last 3 bits, we know that they are parity check bits that we add them to the data to make a code word. And how do you know that there are 4 bits for data? Because the received sequence is 7-bit, right? 7-bit. And G is 1, 0, and 1, so G is 4-bit. When G is 4-bit, it means that n minus k equal to 3 because the number of bits of G is equal to n minus k plus 1. So the code word, the received sequence is 7-bit and n minus k is 3-bit. So therefore the data has to be has to be 4 bit. Okay, so you have n equal to 7 bit, right? Number of the bit in the code word or in the receive sequence, n minus k equal to 3 bits. Okay, so k must be equal to 4 bits. Therefore, the receive sequence that you have 1 1 1 0 1 0 0. You know that the last 3 bit is n minus k priority check bit. So these are data bits. So you will decode. When you decode, you will have at the decoder, you have 1 1 1 1 1 0 0 coming in, and you will give out 1 1 1 0 as the decoded data. Okay, the decoded data. So the decoder will do the remainder of R over G. Okay, if it is 0, you take the first 4 bit out as a data. Okay, the second method is by polynomials. Okay, you do the similar thing. Okay, by putting the binary coefficient. Okay, as the binary value as the coefficient of the polynomial. So when gx is 1 1, okay, gx is 1 0 1 1, right? The leftmost bit is 1, and this is x cubed. Okay, because the least significant bit is. Okay, let me show you this. Gx equal to 1 0 1 1. Okay, this is least significant bit. This is most significant bit. So the least significant bit is degree x to the 0. And this is x to the 1, x squared, and x cubed. And therefore, gx, sorry, the sequence g is this. So gx is x cubed plus, okay, you don't have x squared, right, because it's 0. But you have x1, so x plus 1. Similarly, the receive sequence, okay, is 1 1 1 0 1 0 0. So Rx equal to this is the least significant bit, okay? So x0, x1, x squared, x cubed, x to the 4th, x to the 5th, and x to the 6th. So you have x to the 6th plus x to the 5th plus x to the 4th plus x squared. So this is the receive sequence, okay? Only the term that have the value, the coefficient of 1, okay? We have the value. Okay, so when you have the receive sequence, you can divide it by the generator polynomial. Okay, divided here by gx, sorry, x plus 1, right? So you have this one is x cubed, x to the 6th plus x to the 4th plus x cubed. Okay, so you get x to the 5th plus x cubed plus x squared. So this one plus, again, when you add them together, they are 0. Okay, you minus or you add them together, they are 0 because this is modulo 2 addition. So you get x cubed plus x to the 5th plus x cubed plus x squared. So this is 0. Okay, so remainder equal to 0. No error is detected. Okay, no error is detected. So what is the data? The data is the first 4 bit, right? So when you have, this is Rx, okay? So the data is again the first 4 bit is the decoded data, the same thing. The last method is chip register circuit. In this case, you have to feed the chip register instead of the data sequence, okay, to the chip register circuit, and you have to input on the left. If you remember, in the last circuit, okay, when you encode it, you put the data on the right, okay. This M on U is the same, okay. It's data on the right, because we want M to be we want encoding, we want to find the remainder is okay. You want to shift this one, okay, n minus k bit, okay, first before you divide. So you put so this is a circuit. So you put the data, okay, U or M on the right hand side because this is x to the n minus k, okay, position. Okay, at this point is n to the minus k position. The left hand side is the x0 position. This is encoder. But at the decoder, you divide, you find the remaining of R over G. Okay, so you have to put R over here because this is x to the 0 position. Okay, and you didn't multiply R with anything, so you have to put it here on the left hand side of the circuit. Okay, in this case, R is 1110, 100. You always, okay, put the most significant bit into the circuit first. Okay, I will show you. Again, G, this is the same code, so G is the same. Okay, Gx is x cubed plus x plus 1. Okay, or 1 plus x cubed if you want to write in the circuit. Okay, so you have 3 blocks. And this one has a line x0, x, okay, this one coming down like this. The difference is that you have R getting in here on the left hand side. So the circuit will be like this, okay? Now, always input the most significant bit first, okay? The same thing as encoding and decoding, okay? Always input the most significant bit first. So R is what? R equal to 1, 1, 1, 0, 1, 0, 0. So I put 1, 1, 1, 0, 1, 0, 0. Okay? So at first, 0 is initialized, okay? Then when 1 coming in, 1 plus, okay, this is shipped here as a 0, okay? So 0 plus 1, 0 plus 1 is 1, right? Okay? Then 0 plus 0 is 0. This is just shift, okay? Now to use the technique, okay, of the boundary, we can put it like this. Okay, if you cross the boundary, you have to be careful. But if you don't cross the boundary, the value always the same. Then 1 getting in again. When this one getting in, what happened? The shift feedback bit is 0 again. So 0 plus 1 is 1. Okay, so this is go down as 0. So this is the same. Okay, then this one. Oops, sorry, the same. This is the same. When 0 is shift, okay, so 0 plus 1 is 1, okay? So again, 0 is shift, so this is the same. Okay, then 1 is shift here, 1 is shift here. 1 plus 0 is 1. Okay, 1 is shift here, so everything is changed at the boundary. Okay, change at the boundary. And this one is 1 again. Okay, then 0 is shift. 0 is shift over here. Okay, 0 is shift over here. 0 plus 1 is sorry, 1 is shift. 1 is shift over here. At this point, 1 is shift over here. 1 plus 1 is 0. Okay, so 1 is shift over here, change the value. This is the same value. Then 0 is shift, 0 plus 0 is 0. This is the same. 0 is shift, 0 plus 0 is 0. Okay, so this is the equal to the remainder of R over G. Okay, and it's equal to 0. Okay, this means that no error is detected. So the decoded data is R1110, which is the first 4 bits of the received sequence. Okay. Okay, you may want to try example 1 to 3, okay, by using the same generator sequence, okay, but change the received sequence so that it contains some error. For example, since the code word is 1110, 100, you can have the received sequence, okay, changing one bit, okay, maybe the second bit. If you change the second bit, the received sequence will be 1010100, okay. So and then you input this one into the circuit again, okay, to see that the remainder is not 0, okay. So this means that you detect the error. Now, in order to find, this is basically to detect the error. There are another class, okay, that I'm teaching about error coding, channel coding or error correcting code, okay. In that case, we will study a lot of how to find the generator sequence, how to find what is the property of different code, okay, like the BCH code, the Lee-Solomon code, and the cyclic code, the priority check code, something like that, okay. Now I want to show you a little bit, okay, on how you detect the error, okay. So let's look at this. Okay, you have this, right? Okay. We usually put R here, right, in order to get the remainder. Now, suppose I send code word equal to all 0, okay, or equal to 0, 0, 0 like this. So every bit is 0, okay. Because my data is 0, then when I encode the code word, then all the priority checks is 0. So when I receive it, okay, the receive sequence is like equal to the code word plus the error, right? Receive sequence equal to code word plus the error. If my code word is 0, then in this case, the receive sequence is equal to the error sequence, okay, if this is all 0 code word. Okay, so I will show you something, okay, on how to give you a sense of how we can correct the error, okay, for the priority check code, a simple priority check code, okay. So if I have the error, okay, in the first position, if my error look like this, okay, in the first most significant bit, okay, so I will have the receive sequence look like this too. So I will put here, okay, so I put the first bit as the most significant bit into the circuit, okay, okay, so what do I have? Okay, first I initialize 0, 0, 0, right, and then when this one, okay, I have the boundary here. Now, when one coming in, what happened? This one is shipped over here, okay? Okay, so you get, you know, actually, since these are all 0 and it will shift into 1 by 1, okay? And feedback is always 0. So the first 3 bit, okay? After this, you will get, after the 3 shift, okay, you will always get this. Okay, because this one is get in, okay, this one is get in and then shift into the back, this one is get in, shift into the back, this one is get in, shift into the back, okay. But anyway, let's do it 1 by 1. So 0 plus 1 is 1, okay, this is shift 0, 0, and then 0 plus 0 is 0, right, and 0 feedback here, so 0 plus 1 is 1, this is 0, okay. So when 0 put in here, plus 0 is 0, this one shift to 0, this one is 1, okay, the same as I was saying. Anyway, after this, 1 plus 0 is what? 1 plus 0 is 1, right? And 1 is the feedback here, so the value here is changed. Okay, so, okay, at this point, 1 plus 0 is 1. 1 feedback here, 1 plus 0 is 1, and 0 is shifted here. Now, 0 plus 0 is 0, right? So, 0 feedback, so this is the same. Now, 1 feedback, okay, 1 plus 0 is 1. 1 feedback, so this changed, okay, this is the same. 1 plus 0 is 1. 1 plus 1 is 0. Okay, so you can see that we have the values here. If I want to write these values, I will have something like this. I have a table. Okay, error values and syndrome, okay. I will tell you about syndrome in a little bit, but let's look at this first. If the error value is 1, 0, 0, 0, 0, 0, okay, like this, the syndrome, this is the syndrome. Okay, the syndrome, that is like the remainder of syndrome equal to the remainder of R over G, okay? So you divided the remainder, we call it syndrome. Okay, so in this case, the syndrome is 101, right? Okay, now, if you have another error, suppose my error is 01, 0, 0, 0, 0. I mean that only 1 bit, okay, but it's in the second bit position, okay? What happened is that it's like I will input 0 here, okay? I input 0 here, okay? Now, what happened is that the first 0 getting in, everything is the same, right? Everything is the same. When this one getting in, you get this. When the last bit getting in, you get what? You get this. So this is the remainder for the error values of 0, 1, 0, 0, 0, 0. So it's 1, 1, 1. This is the value. Now, if I use another error, okay, so my error is like this. And again, the same as my receive sequence, okay, because I send the code word as 0. I will get 0, 1, 1, okay? You may have, you may be able to guess the next value, okay? So the next value, when I put 1 over here, and I have 2 zeros. Sorry, in this case, I have, sorry. Actually, missing 1 0 here because it has to be 7, right? Okay, in this case, I will have, when I have 3 zeros coming, I will have this line, okay? 1, 1, 0. And in this case, I will have, when 2 0 coming, I will have this line. 0, 0, 1. And the other case is 0, 1, 0. The last case is 1, 0, 0. Okay. If there is no error, as a special case, if there is no error, okay, error equal to 0, what you get is all 0. Okay. Now, we have this table, and we can use this table to correct our error. Okay. So when you have this table, you can use this one. Okay. Now, suppose you have R coming in, okay? R coming in, and R is, so this bit is wrong. Okay, have an error in this bit. This is the same as our last example, okay? If the code word was 1 1 1 0 1 0 0, right? And this bit is wrong, so we have the receive sequence like this. If it's wrong in the second bit, okay, and if you do the remainder of R over G, you will get the syndrome, okay, the same as the second bit here, which is 1 1 1 always, okay. If you get the syndrome of 1 1 1, and then you look at the table here, the syndrome is 1 1 1. So what is the error value? The error value is at the second bit. So the correct the receive sequence, okay, that has been corrected would be 1 1 1 0 1 0 0, okay, because we know that the error is in the second bit. So since binary value has only 0 and 1, so if 0 is wrong, then the correct bit has to be 1. And what is the decoded data? The decoded data are the first 4 bits, okay, so 1 1 1 0, the same. Now, why can I tell you that if it's error in the second bit, it's always that the error is always have the syndrome of 1 1 1. This is a little bit beyond the scope of this class, okay, but I can tell you this, that the code word, okay, all code words have no remainders if you divide it by G, okay. So the effect of the syndrome depend only on the errors and not the code word. All code words have no remainder. So remainder is affected by only the errors. So if the error is in the second bit, okay, always it will have this syndrome 1 1 1. If the 0 is in the first bit, always it will have the syndrome 1 0 1. And you can try by yourself, okay, by changing the receive sequence into the error in the other bit to check whether this is true. You can also change the data into something else. You can change the data into maybe 0 1 1 0, something like that, and then you find the code word, okay, and you transmit. Let's see if there is an error coming in, coming into the decoder, and the decoder will check the syndrome and see what happened, okay. So what you should do is that you should use another U, okay. You can use U, for example, 0 1 0 1, then you find the code word V, right? Then you add some error and you get the receive sequence R, and then you find the remainder of R over G, okay, to get the syndrome and check whether this is the same, okay. So this table works for the code that Gx equal to 1 plus x cubed, okay. So if it's different G, okay, the table will be different, okay. So this table is related to this generator polynomial, okay. So this is some of the idea on how to correct the errors, okay. A lot more, there's a lot more details on this, but we will not cover in this class. Thank you. So this is the end of lecture 11. For next time, we will talk about chapter 6, okay. In lecture 12, we will start the new chapter about data link control protocol. Thank you.